Welcome to Design of Concrete Structure course. So this is lecture number 14. So here we'll be discussing the two-way slab. So if you recall last lecture onwards we have started the slab design of slabs. So we have discussed how to design the one-way slab. So today we'll be discussing two-way slab. So before starting, let me just recapitulate what we discussed in the last class. So which one is the two-way slab? So we understand there are actually two types of slabs. So let's quickly draw a slab. So a slab is either maybe square or rectangular or whatever it may be shape. Basically based on the dimension of the slab, we classify the slab into two parts. Either it is one way slab or it is two way slab. So for example, this is Lx dimension and this is Ly dimension. So if Ly by Lx, that is a ratio of two dimension, if it is greater than 2, then we call it is one way slab. So if it is this true, then it is we call it one way slab. So that means based on the ratio of two periphery, we call it either it may be one way or it may be two way slab. So if Ly by Lx is more than 2, then it is one way slab, and if Ly by Lx is less than or equal to 2, we call it is a two-way slab. So in the last lecture we have discussed in details how to design the one-way slab. There were 6 steps involved in it, and step by step we have performed all the experiments. So in this experiment or in this lecture, basically we'll be discussing about how to design the two-way slab. So let's get started. So two-way slabs are mostly subjected to uniformly distributed load, and primarily it resists by bending about both the axes, unlike one-way slab. So if you recall, in case of one-way slab, what we discussed. So for example, this is a one-way slab. So one-way slab means always one dimension will be almost more than double to another dimension. So this is Lx and this is Ly. So when Lx, so here if you can see Ly by Lx is obviously more than 2 because Lx is comparatively very short compared to Ly. Okay, so this is the one-way slab. So primarily one-way slab means the bending will be happening about shorter axis. So this type of bending will be happening. So if you see the cross section here, then this is the figure, this is the deflection shape you will get it. So primarily the deflection will be happening in one side of the slab. That's why it's called actually one-way slab. But in case of two-way slab, the deflection will be happening in both the sides. Along the x-axis as well as along the y-axis also deflection will be happening. So normally based on this bending, and the slab basically takes the load of a structure or load of live load, dead load, whatever it may be. However, as in one-way slab, the depth of two-way slab should be also checked for the shear stress to avoid any reinforcement for the shear. As we discussed earlier also, normally we do not provide any shear reinforcement in a slab because the shear stress on a slab is very low compared to beam. Okay, so because the shear stress is very low, the shear reinforcement may not be required to provide in a slab because the concrete or reinforced concrete itself has some capacity to withstand the shear force. So normally the shear stress comes out to be in a slab very low. Because of that, we do not need any additional shear reinforcement. The inbuilt reinforced concrete can take care about the stresses. So in just we have to check it whether the stress is less than the permissible limit or not. If it is fine, then it's okay. Otherwise we have to redesign, means we have to increase the depth or whatever it may be. So we have to redesign the section. So moreover, these slabs should have sufficient depth to control the deflections. Okay, so depth we should provide. Thus the strength and deflections are the requirements for the design of two-way slabs. So now let's get started. Now design shear strength of a concrete. So how much will be the shear strength of a concrete? So if you see this figure, so here I have considered two strip. One is this AA strip you can see, and another is BB strip. So one AA strip is along the y-axis, whereas BB strip is along the x-axis. Okay, so now how we discussed in the last class also how the loads are transferred to these beams. So basically, if you consider this is a slab, and this slab is resting on four beam, 1 2 2 3 3 4 and 4 4 1, right? These four beams are there in four side. So this entire slab is resting on this four beams. Now, whatever loads are applied on a slab, basically this load is transferred to all four beams. Now, the question is how much load will transfer to how much beams and which beams? That is the question. So, what we'll do in two-way slab, basically as per IS 456, so that is the load distribution of a slab. So we have to draw 45-degree line from here at point A and again 45-degree line here at point B, and both the lines will be intersecting at some point. So here you will get one triangular shape. Similar process you will do it for here also, 45-degree angle for both the sides. So these two points will meet at some point here. So you will have these two, one triangular portion, another triangular portion, and two trapezoidal portion. So whatever load is coming from this triangular portion, this entire load will be transferred to this beam 1 1. Similarly, whatever trapezoidal portions load is coming, that load will be transferred to this slab. So that's how the load distribution is happening. Similarly, this type of here whatever load is transferred generated, that load will be transferred to this beam, and from this trapezoidal shape, whatever load is developed, that will be transferred to this beam. So that's how the typical load distribution on a slab that we consider while designing and while analyzing the beam or slab. So now here you can understand that this angle is basically 45 degree, right? So this as this angle is 45 degree, so you can imagine this is a triangle. So this is a small triangle you can consider. So this angle is 45 degree means this angle is anyway 90 degree. Okay, let me draw it here quickly. So you can consider this is a rectangular beam. So this one is a not sorry triangular portion. So in triangular portion, basically this angle is anyway 90 degree. This is 45 degree, so this angle also must be 45 degree. That means this angle is 45 and this angle is also 45 degree. That means whatever length is there, this length and this length both are same. Okay, as the angle is also same. So whatever is that AA is what? AA is the length of this strip. So AA is equal to half of BB. So BB is entire length, but half of BB is how much? This much is half of BB. So same thing here, half of BB. So AA is equal to half of BB. So what we can see from the trigonometry is that length of AA is equal to nothing but half of BB, right? So BB is what? So LX. BB is nothing but LX. So half of LX, right? So now we understand, just from trigonometry we got this expression. So now let's understand the shear stress, where the shear stress will be maximum. As we have seen in case of normal cantilever beam or maybe simply supported or fixed, whatever may be the type of the beam, always shear force is maximum near to the edge. Okay, near to the end of the support. So let me for your reference, let me draw it quickly. The if you have a beam, or it may be cantilever or whatever may be the beam. So if the loads are applying UDL or point or whatever it may be, so the shear force diagram of this beam will be something like that. Okay, so you can see the shear force always maximum near to the support, right? Near to the edge or near to the support, shear stress is maximum. Similarly, here also the shear stress will be always maximum near to the support, right? Near to the edge. So that's why we consider only a section near to the support AA. Okay, so the shear stress will be, shear force VU will be, W is what? UDL multiplied by LX by 2. Why? Because at A only this portion shear stress will be maximum, right? Near to the support, always near to the support. So this height is how much? This height is Lx by 2. So W into Lx by 2 is the shear force. So maximum shear force basically BU. So maximum shear force will be developed near to the support, right? So that is the value for that. So VU is equal to W into Lx by 2. Either it may be X direction or Y direction, whatever it may be. So the force will be something, the maximum shear stress will be this much. And tau v is shear stress. So shear stress will be what? Shear force by cross-sectional area. So shear force is what? Vu is the shear force by cross-sectional area is B into D. If you consider a strip, so it has some depth. So that is D, and width is normally 1 meter we consider in a slab. So that is B is 1 meter. So whatever it may be, so that tau v will be generated. It can be computed. So this tau v is nothing but shear stress, and the shear stress value should be less than or equal to the shear stress developed by the concrete itself to avoid any shear reinforcement. Normally we do not provide any stirrups on a slab, right? So that's why we have to check it whether tau v is value is less than the RCC strength capacity, shear strength capacity or not. So that's how we deal with the shear stress on a two-way slab. So now let's see the how the bending moment will take care about the slab. So normally two types of in case of two-way slab also there are two types of two-way slabs are possible. One is restrained slab, another is simply supported slab. So what is restrained slab? So as the name suggests, you can tell you can understand that restrained support slabs means which the slabs are restrained, means it is restricted to move around. So for example, let me draw a quickly a slab. So this is a slab, small slab I have considered. Okay, so here it is supported by four columns or four beams also is there. Okay, so this is a small slab, you can consider it is two-way slab basically. And whenever loads are applied here at the middle, for example here you have applied very high concentrated load, what will happen? This slab will try to buckle it, right? Means this middle portion will want to go down, whereas this top corner wants to go up, is not it? So you can imagine, you can take a paper and you can find it out that if you apply the force at the center of the paper, the four sides or four edges or four corners, basically four corners of the paper will come out. So these four corners will come out and middle portion will go down, right? Because we applied force at the middle, so middle portion will go down, whereas this four portion or four corner will come up towards up direction. So that is by default. If you see that type of slab, you will we call it simply supported slab. Means this slab is simply supported on a four beam. So there the corners are not restrained, means not connected to the beam. It is simply just supported. The slab is simply supported on four columns or four beams. So in that case, if we apply any force here at the center, the four corners will be trying to come up, whereas middle portion will be trying to come down, is not it? So this type of slab, we call it simply supported slab. But in general, if you see where you are sitting in any multi-story buildings, what we do, we cast this beam, column and slab monolithically, right? Together we cast it. So that means these corners are actually fixed, and if you apply middle some load, these four corners won't come up. Okay, so it will be in their position only. So depending on the fixity, the four corners will be in their position itself. So that type of slab we call it restrained slab. Means all four corners are restrained, for going up, going to lift. So this is the two types of two-way slab. We'll discuss how the bending moment calculation can be done for the two-way slabs. Anyway, shear force calculation for both the types of two-way slabs are same. So that is common for both the slabs, whereas bending moment will be different for two types of dimensions, right? Because restraint means here we'll have the fixed support, right? All the four corners we have fixed support, whereas because of force of fixed support, that torsional reaction will be generated at these four corners. Whereas in case of simply supported slab, the four corners are not restrained. In that case, there won't be any so reactions, moments in the four corners. So the design will be very simplified. So let's now see how to compute the bending moment in case of restrained slabs. So the restrained slabs are those whose corners are prevented from the lifting due to the effect of not torsional moment. So these torsional moment, however, are not computed as the amount of reinforcement are determined from the computed areas of steel due to the positive bending moment, depending upon the intensity of the torsional moment of the different corners, right? So basically, restrained slabs are what happens. Restrained slab means these four corners will be restrained for the upliftment. So these four corners won't be going up. So in that case, the near to the corners, basically you will have negative moment, as I discussed earlier also, like, right? For example, if you have a fixed beam, you can imagine this with a fixed beam. So we have discussed many times fixed beam, we know with a point UDL or something like that. So what is the bending moment diagram for this beam? So bending moment diagram will be something like that. So we'll have negative bending moment near to the support, whereas positive bending moment at the middle span. So same thing, you can see it here also. The middle strip basically will have positive bending moment, whereas the edge strip you will have the negative bending moment. Okay, so normally what happens that as per our IS 456, basically if the total length is LX or total length is LX, that means only 3/4 of LX we call it middle strip, and L by 8th portion we call it its edge strip. Similarly, both sides L by 8 is edge strip. So the slab is total slab, this one, right? So this two portion we call it edge slab. So the length is to, L by 8 portion we call it edge slab, and negative bending moment will be developed in this edge itself. Similarly, this is for span Lx and this is span Ly. So Ly means this is the edge strip, you will find it out. Okay. Similarly, at the center you have the positive bending moment. Same thing. So here is for span Lx, right? Lx means what? Our considering beam means strip is in this direction. Okay. Similarly, here our strip is something like that. Along y direction. Okay. So in case of one-way slab, we designed only one direction, right? We considered one direction beam and then we designed it as a slab. But in two-way slab, we have to take two beams. One is along x-axis, another is along y-axis. So two strips we have to design it, and based on that we have to provide the reinforcements. Okay, so now how much is the maximum, how much is the bending moment developed in the 2A slab, that you will get it in the table number 26 IS456. So in the table number 26 IS456, if you visit, you will find different types of slabs, different Lx by Ly ratio. With that, different types of slabs, it will give you which type of, what is the coefficient of alpha x. So once you know the alpha x from table 26, you can easily compute mx equal to alpha x into WLX squared. So alpha x value you will get it from the IS456 table number 26. And similarly, my also can be computed. Alpha x value will get it from this expression. Similarly, you plug in W is the total, how much load is coming on a slab, and Ly is the total length along the y direction. Okay. So once you know all this, mx and my can be computed, and alpha x can be get from this table number 26 IS456. So just like a recapitulation, in one-way slab, basically you have designed the slab for one direction, right? So let me draw it here. So in case of one-way slab, basically, you know, the we have considered the strip along the x-axis. This is x along the shorter directions. Okay, so this is Lx. So we consider a strip, a beam strip of something like that, and that we have designed it. Right, that is a one-way slab. But in case of two-way slab, we have to consider x direction as well as y direction also. So one more strip we have to consider along the y direction, and both the strips we have to design it. Okay, and this is along the y direction, Ly. So one-way slab means only one beam, one strip design, whereas two-way slab means both the strips you have to design it. And so maximum bending moment generated in the each strip can be get we can get it from table number 26 IS456, where the alpha x values are given based on depending on different Ly by Lx value. The alpha x values are given, that we have to consider it. So, and next case is for the simply supported case also, that you will get it in the table number 27. Table number 26 you will get it for the restrained slabs, whereas table number 27 you will get it for the simply supported case. What is the moment coefficient alpha x value? Okay, so now you can ask, so how these values, alpha x values, are computed? Okay, so you in table you will get it the ready-made values, but you have to understand basic concept also, how these values are computed. So basically what we have done is, basically we have considered two strips. So one strip is along x-axis and the strip is along y-axis. Okay, and each strip has 1 meter depth, right? 1 meter width, right? We consider it as a beam, 1 meter beam. So now from this axis we find it out, maybe we consider a point, intersecting point between these two strips is this point, for example P, right? So once the load are applied in the slab, what will happen? This entire slab will undergo deformation. So the deformation at this point we compute based on this strip. So based on this x strip we compute what is the deformation we get it at this point. Similarly, this along with this strip we again compute what is the deformation we get it here also, and both the deformation should be same, right? Because the slab is a combined of both the strips. So whenever you apply the whatever deformation will be there in this point, that will be same if you consider a beam in this direction and both the directions, right? So you will have two equations, and we can get it what is the mx value for this moment, bending moment about this strip and bending moment about this strip. Like that, all the tables 27 and 26 are computed, and all the ready-made values based on Ly by Lx are given in the table. So for calculation of maximum bending moment, positive bending moment as well as negative bending moment, we can easily refer the table and we'll get the coefficient quickly. So in case of simply supported slab, there is no negative bending moment, only positive bending moment will be there all along the slab. Whereas in case of restrained beam, that is last case, you will have the negative bending moment also near to the edges. Okay, now let's see the design consideration. So design consideration will be same initial first six considerations. If you recall, in the one-way slab we discussed in the last lecture, so here total six design considerations we have considered. So here also in 2A slab also the all the six design consideration A to F are applicable, in case of 2A slabs except B. So except the second consideration has small changes here in the 2A slab. So that's why B is not there, C, D, E, F, right? Remaining all five are same, but B is different. So that's why only B I have explained here. Okay, however, the effective span to the depth ratio, if you see in one-way slab, we have used some other clause, but here code is mentioned for the two-way slab, you have to use some other effective span by depth ratio, and that you will get it in the clause number 24.1 IS456. So these are the following notes you will get it from the IS456. So in case of simply supported beam, the values has to be taken 35, that is effective span by effective depth ratio. For in case of simply separated beam for 2 slab you have to consider 35, and you will get these values in this clause number. If you visit this clause S456, you will get these values. Okay, so these values are only valid as the for the span up to 3.5 meter and the mile steel. If the mile steel is used, then only these values can be used. But if you are using any HYSD bar, if you are using, so these values are actually applicable for mile steel, right? It is mentioned. But if you are using HYSD bar, for example, if you want to use FE 415 or FE 500, so this grade of steels, basically whatever value you get it, that has to be multiplied with 0.8 coefficient. Okay, so whatever value you get it, you multiply with the coefficient, and then that will have to be used in case of high HYSD bar. So these are six design considerations. So five design considerations are same as one way what I discussed in the last lecture, only change with the effective span to depth ratio, that also you will get it in this clause number. So now we'll see what is the design steps for that. So design of 2S slab, the procedure for the 2S slab will have the 6 steps, right, as mentioned in the earlier section. So in 1 slab also we have designed a total 6 steps were there. So exactly the same 6 steps you have to follow it in case of 2S slab also. But one extra, that is step number 7 will have extra in this 2S slab. So that step number 7 is nothing but for the restrained case, when the four corners will be coming out. So to restrain the four corners in its original position, we have to apply additional reinforcement. Okay, so that is the step number 7, which deals with the torsional moment. So the initial first 6 steps whichever we mentioned for the one-way slab are same, except the bending moment and shear force calculation has to be used table number 26 and table number 27, right? These two we have to use it. Okay, in case of one-way slab we have used table number 12 and 13 if you recall, but here for two-way slab we have to use table number 26 and 27 for the bending moment calculation part. And only additionally step 7 will be coming here in two-way slab. What is this step 7? So step 7 means basically the slab is subjected to, when the slab is subjected to load, the four corners will try to come up, right? It will try to lift up. So to keep the slab in original position, we have to provide some additional reinforcement at the four corners, right? So that four corners, how to provide that is mentioned in the step number 7. So here first 6 steps are same, so I am not elaborating again all the 6 steps. You can refer the last lecture, whereas only step number 7 I will be discussing here in this lecture. So the step 7 is determination of torsional reinforcement, right? So you understand this is maybe a very big plan of your building, whereas beam columns will be there. So this is one slab panel, this is another slab panel, another. So here total 6 slab panels you will find it. Okay, so each slab panel will have that the slab design will have different. So because if you see this slab, so this slab, two sides are discontinuous, right? So this is edge, so the slab is not continuous in this direction as well as this direction also, right? So this is one type of slab panel where two sides or two edges are discontinuous. Whereas if you consider this slab panel here, only one side is discontinuous, whereas this side is continuous, this side is continuous, this side is also continuous. So C2 has only one side discontinuity. Similarly for the C3 also, it will have also, maybe C3 may be the inner panel. So in that case, the all four sides won't be discontinuous. I mean all four sides will be continuous if C3 is inner panel, means at the center, right? So maybe I'll draw it quickly. If you add one more panel here, what will happen? So one more panel I have added in the slab. So in that case, you will find these three types of panel. So one is this corner panel where two sides are discontinuous. Another panel you will find only single side is discontinuous, whereas three side is continuous. And the middle panel you will find all four sides are continuous, right? So these three types of panels you will find it in a slab. But the torsional reinforcement has to be provided the corner reinforcement, the in case of C1, C2 or the corner edge panels, because the edge panel is trying to come up while you apply the load on a slab. So this edges has to be come up, okay, lift up when you apply the load. So that's why the we have to provide the torsional reinforcement at these edge panels, not the middle panel. So middle panel anyway it won't lift up. So that's why no need to provide any corner reinforcement in four corners in the middle in case of middle panel. Whereas all the edge panels you have to provide the torsional reinforcement. Okay. So that how much we have to provide it at the in case of torsional reinforcement, that is given in our IS clause IS 456 clause number D 1.8. D, I think annexed D 1.8. If you go IS 456, you will get the criteria for C1, means at the corner C1 how much torsional reinforcement you have to provide it at this corner. So at corner C1 where the slab is discontinuous on the both sides, so you can see both sides is discontinuous, the torsional reinforcement shall be consist of the torsional reinforcement you have to provide it at the top and the bottom bar, each with layer of bars placed parallel to the sides of the slab and extending minimum distance of 1/5 of the shorter span of the edge. So what is mentioned? So this clause you will find it in the provision, you will find it in this clause. If you visit IS 456 clause D 1.8, you will get this writings. Okay, what it said. C1 means what? C1 means corner range, corner panel, right? Here both the sides are discontinuous. So in that case, you have to provide reinforcements parallel to the edge. So something reinforcement you have to provide along the both the axis. This is along one y axis and this is along x axis. Also we have to provide it. Something like that. This grid point reinforcements you have to provide it. And again both the sides means if you have a cross sectional area, let me draw it, a cross sectional area of this slab. So reinforcements are provided at the bottom and at the top also, both. Okay, and it is in a gridded manner. So you can imagine that this gridded manner reinforcements are provided at the top as well as at the bottom also, both sides. That is to restrain the slab in its original position. Otherwise, this portion will come up, right? This portion will come up at the after you apply the load. So that is the C1. How to design the C1? All the design criteria are mentioned in this clause. Now in case of C2, what will happen? The three sides are continuous, right? Only one side is discontinuous. So whatever reinforcement you have to provide is half whatever you provided in case of C1, half amount of reinforcement you have to provide it in the C2. And here the bars are provided along only one direction, incomplete. But here we provided both the directions, right? But in C2 we have to provide in only one direction to restrain the beams or the slabs in the original position. And in case of C3, the is contained by edge over both which the slab is continuous. So slab is continuous here also, here also, here also, here also, right? All four sides these slabs are continuous. So that's why the tensional reinforcement need not to be provided as stipulated in the IS clause number. If you in this one, if you visit IS clause number this one, you will find that for C3 case, means if the panel is at the middle panel, then you need not to provide any torsional reinforcement at the corners. Whereas if the panels are near to the edge or at the edge, basically you have to provide the reinforcements. In case of when the if the C1 case, you have to provide four layers of reinforcement. Okay, one layer is a top reinforcement towards X. Then second layer is towards Y, top reinforcement. Then again third layer is towards X, bottom reinforcement. And fourth layer is towards Y, bottom reinforcement. Okay, so these four layers of reinforcement you have to provide it in case of C1, whereas C2 means only if one side is discontinuous, then we have to provide two sides of two layers of reinforcement. So that's how the step 7. So up to first 1 to 6 step is same as one way slab, but only varies is step 7. So now if you see, this is the detailing of reinforcements. Okay, so this is a slab panel you can consider. This is C1 case. C1 case means two sides are discontinuous. How you can understand it? So see, this is a slab, right? So this side, along this side, if you see, this is continuous. So this is the symbol means this side it is continuous. Whereas this side also you will find this type of symbols along the y-axis. So this side also it is continuous. Whereas this side you won't find any this type of symbols, right? Continuity symbol. That means these two slabs are discontinuous, whereas these two slides are continuous, means slabs are continuing here also, here also. So this is a typical C1 corner, whatever we have seen in the last slides, that is C1 panel, you can consider this one, where we have to provide the 4 layers of reinforcements, right? So this is bars along the x-axis and this is bar along the y-axis, it is shown. So in the along the x-axis means you have to provide these bars b1, b2. So these two bars you have to provide it here. Whereas along the y-axis, BB means bottom reinforcement. Okay, so bottom along the LY is this B1, B2, whereas along the X you have to provide B5, B6. Okay, this B means bottom reinforcement, right? So total 4 bottom reinforcements. So B1, B2 along these two vertical bar, and B5, B6 is this vertical, this horizontal line. So you can see how much spacing you have to give and everything, all the values are given as per our IS code. Okay. So these 4 bars B1, B2, B3, B4, sorry, B1, B2, B5, B6. So these 4 bars are provided to take care about the positive bending moment, right? So now you understand in a slab basically two types of bending moment will be generated. One is positive bending moment, which will be at the middle of the span, right? That's why at the middle of the span, this is edge, these two are edge, but at the middle we provided bottom reinforcement. Okay, so B1, B2, similarly here also in the middle we provided B5, B6. So in actual beam, both the reinforcements are provided in the same slab, right? But here I have shown just in different cross sections. One is along the x-axis, this is the 2 bar. Along the y-axis you will find b5, b6. Okay, and now the corner reinforcement. So negative bending moment occurs near to the edge, right? Near to the edge the negative reinforcement occur. So negative reinforcement we provide top reinforcement, right, for the negative bending moment. That is T1, T2, T3. You can see this 3 bar top reinforcement. T means top reinforcement, 1, 2, 3, 4 are provided at the edge of the uh, slab, right? And this is the top reinforcement. Similarly here also you will find T9, okay, sorry, T4, T5, T6. Okay, so T1, T2, T3, T4 is vertical one, T5, T6 is also the vertical one reinforcement, sorry, horizontal one. So this four, this one is T5, T6, and T4. So here total 6 top tension reinforcements are provided: T1, T2, T3, T4, T5, T6. You can understand that these top reinforcements are always at the edge of the slab or corner of the slab, because negative bending moments are developed always at the edge of the slab. Okay, now you understood this one. So total, like that, total 18 reinforcements normally we have to provide in the corner. So total B1, B2, B3, like the total B8. So total 8, and near to the corner also. If you see these corners, edges we have provide in the corner, we have to provide both, right, bottom and the top. So corner B7, B8, bottom reinforcement. Similarly, similarly here also T7 and uh, T9 also are provided. These are the top reinforcements. So total basically 18 reinforcement we provide. Top reinforcement T1 to T10 you will find total 10 top reinforcements, and bottom also B1 to B8. So total 8 bottom reinforcement we provide in case of slab. So that is the typical detailing of slab. That's why when you visit next time in a slab, before casting, after the reinforcement done, then you will find this type of grading part in a slab. And where now you understood why these bars are provided and how many number of bars minimum has to be provided, all these things parameters are mentioned, and what will be the spacing. So some bar will be continued. For example, if you see this B2 bar, so B2 bar will be from here to up to here. So some portion it goes, then we have to curtail it, we have to cut it out. Okay, why? Because this is bottom reinforcement, right? So bottom reinforcement is provided only for the positive bending moment. So positive bending moment is not there near to the support. Then why to continue this bar again towards the support? No need, right? because positive bending moment we provide bottom reinforcement for positive bending moment, and positive moment is maximum at the middle, right? So that's why this bar is continuing in the middle, but near to the edge it is discontinued. We just curtail it after certain point, and that distance also given to us. It is 0.29 something lx also. So these values we will be getting in the highest code. Okay, all these details. So now the same figure, if you take the cross section at 1 1 and 1 2, you will find all these 18 bars, just now whatever I mentioned it. Okay, so this is a corner panel, right? You can see the top reinforcement with T1, T5, T6, whereas bottom reinforcements are B1, B2, B5, all these things. And that is a simple section view of earlier figure. At section 1 1 you will get this type of section, whereas section 2 2 you will get this type of diagrams. Okay, so now that is the procedure for design of two-way slab. So we have seen total 7 steps involved in design of two-way slab. 1 to 6 steps are exactly same as what we discussed in case of one-way slab, whereas the additional part here in the two-way slab comes out to be the step number 7. The only change is 1 to 6 is same, and only step number 7 is additional here for the two-way slab. So now we will solve a numerical problem quickly. So what is the problem here? Problem is design a slab panel 1. So slab panel 1 you have to design it. Which one is slab panel 1? So C1. So this is the slab panel 1 you can see. So design a slab panel 1 in a figure. To a factored live load is given to us 8 kilonewton per meter square. In addition to the dead load already whatever is there for M20 and Fe415 grade of steel and concrete we are using. The load of the floor finish is 1 kilonewton per meter square. So floor finish is again the tiles or whatever is mentioned, whatever is given, that is 1 kilonewton per meter square coming from from floor finish. The span shown in figure are effective span. So whatever span length is given to us 600 and 400, these are actually effective span. So no need to compute the effective span separately. Whatever the span is given, that is effective span directly. The corner of the slabs are prevented from lifting. That means the corner of the slab, so this corner C1, this corner, this corner, this corner is prevented from slab lifting. Means this is a restrained slab. It is clearly mentioned in the question that this slab is restrained slab. Means all four corners are actually not going to up, going up by after you apply the load. So this is a typical example where you are maybe in a real life any structure, if you see, you will find this type of beams only, restrained beams. So we have to design the panels P, oh no, this one where the loads are applied, and M20 and Fe415 grade of steel we have to use it. So that is our problem. We have to design this panel P1, corner panel. Now you can understand this is a corner panel C1 case. Okay, so this is C1 and this panel is C2, right? Because only one side is discontinuous, right? So that's why C2 is mentioned. And this panel is C1 because two sides are two sides are continuous, those two sides are discontinuous. But if this is the middle panel, right? Middle panel means C3, all C3 you will find, right? Because all four sides are continuous, so this is C3 category. So here whatever question is asked, we have to design this panel. C1 panel we have to design it. So let's get started. So our first step, if you recall, same thing what we have discussed in the earlier one-way slab design also. The first step is selection of preliminary depth of the slab. So from where we'll get it? Again, IS clause number 24.1. There you will find effective depth by effective span by effective depth ratio will be given to us, and our slab is then effective slab is given to us, right? If you go to IS 456 24.1 clause number, okay, then the value for the cantilever beam it is given 35, and for the simply supported case, I think for the fixed case it is 40, right? So our slab one side is fixed, another side is continuous. So that's why we have to take the average value. So 35 is for, I think, for fixed, and 40 is for continuous. So if you take the average, so whatever you get it, that you have to multiply it with 0.8. Why 0.8? Because we are using Fe415 grade of steel, right? As I mentioned in the S456, it is mentioned if you are using Fe415 or Fe500, then whatever value we get it, that has to be multiplied with 0.8, and whatever we get it, that we can consider it as a preliminary design value. So it comes out to be 30. So this gives the minimum effective depth of 4000 divided by 30 is 4000 is what? Lx, right? Lx value is given to us 4000 divided by 30, which is nothing but 133 meter. So let's consider 135 mm depth we are providing. So depth of the slab we considered from the step 1 is 135 mm, and the total depth D, effective depth or overall depth, basically capital D, is this 160. We have to provide minimum 25 mm cover, right? So 25, so 135 plus 25 mm cover will get total 160 mm. So in our step 1 we just assumed, or we preliminarily we find it out, the depth is 160 mm overall depth, and the small d value is 135 mm. So now let's compute the design load and the bending moment and shear forces. That is our step 2. So the design load for 1 meter width. So as we consider slab as a beam of 1 meter width, right? So what will be the width? What will be the dead load coming? So the total length is 0.16 multiplied by, from where we got to 0.16, 1.6 is 0.16 is the total depth, right? Effective depth 160 mm we just computed. So 0.16 we converted into meter, multiplied by 25 is the unit weight of concrete. We'll get it 4 kN per meter square is the dead load coming from slab. So dead load from the floor finish is given to us in the question. It is 1 kN per meter square. So total factor dead load will be 4 plus 1 is 5 kN multiplied by 1.5 is the partial safety factor, right? So we'll get the 7.5 kN per meter square is a factor dead load. And the live load is also given to us 7.5 kilonewton. I think 8 kilonewton live load is given to us, the imposed load. So 8 plus 7.5, so total factor load is 15.5 kilonewton per meter square. Okay, so total design load is this much. So that is now we compute. Now we have to compute bending moment and shear force. So this is a fixed beam, right? So two sides are fixed. That means you will have negative bending moment at the edge and positive bending moment at the center of the span. So negative bending moment, for that you will get it. So if you visit clause number, table number 26, IS 456. Okay, clause number D 1.1 and table number 26.456, and this is our case 4, where the both the spans are, you know, discontinuous. In that case, you will get it these values. Alpha x value is this much for the negative bending moment for the continuous edge, and the positive bending moment for the mid span you will get it this much for the short span and for the long span. So because in each slab there are two span, right? One is okay, let me draw it quickly. So one will have short span and another will have long span. Okay, so these two values are given to us. If you visit table number 26, you will get it all the values. For the different Lx by Ly ratio, you will get different value. So in our case, the Lx by Ly value is 6 by 4, so 1.5. Right? Our problem, it is 6 meter by 4 meter, 1.5. So for 1.5 Ly by Lx value, we have to find it out what is alpha x and alpha y value from this table number 26. So these values you will get it anyway. Okay, 0.075 is alpha x, right? Alpha x into WLX square, you will get mx. Alpha x into WLX square. So we already written the formula here, also I'll write. So mx will be nothing but alpha x WLX square. So this is the formula for mx, right? Similarly for my will be alpha Ly square. So alpha x value we got it from the table, and W value is this much, and Lx already we know 4 meter and 6 meter, right? Lx and Ly. So now we got it mx. Mx means positive bending moment, sorry, negative bending moment, and this one is positive bending moment. Similarly for the long span, this is the negative bending moment and this is the positive bending moment. So here two span, right? So two span means one span will be towards x-axis. So this is one span and this is another span. So both the span we have to design it, right? That's why it is mentioned shorter span and longer span. Okay, so one will be shorter and another will be longer span. So one span will be along one axis, another span will be along another axis. So we have now two values. So for one span you have the positive bending moment and what is the negative bending moment, two values are given. For the another span we have the positive bending moment, negative, and both are given to us. We just computed it. So now step 2 is also over. We know now what is the maximum positive bending moment and what is the maximum negative bending moment. So now let's see the step 3, that is determination of checking the effective depth. Whatever we considered effective depth 160 mm, right? Effective depth is 135 mm we consider in the step 1. That we will find it out whether it is sufficient or not. So we have this formula, right? Beam formula. So from beam design onward, same formula we are using. Mu lim is equal to R lim BD square. So from here D equal to all the values we know. Mu lim is 18.6, right? Maximum positive bending moment is 18.6 multiplied by 10 to the power 6 means we are converting Newton meter into, sorry, kilonewton meter into Newton mm. 10 to the power 6 by R lim. So R lim already we know for AP415 and M20 from the table earlier we discussed 2.7376 into B into D, right? What is B? B is 1 meter. 1 meter means 10 to the power 3 mm, and D we are computing anyway. So D comes out to be 82.02 mm. So minimum D depth required is 82.09 mm. But how much we have provided? We have provided D value is 135 mm, right? So it is more than this one. So our whatever we consider that is sufficient. So no need to read it in the section. Up to this point, step 3 is passed. Now step 4 is depth of the slab for the shear force. Now we have to check it, whatever depth we have provided 135 mm, so that depth is sufficient for the shear force or not. So again for the table 19 you will get a tau c value is 0.28. If you provide even lowest percentage of steel in a slab, which is 0.12%, right? Even if you provide 0.12% of the steel also in a slab, then in that case also the tau c value, the capacity of the shear of the slab is 0.28 Newton per mm square. Now we have to compute how much shear stress is coming into our beam. If our beam shear stress is less than this value, then the slab is safe. But if the shear stress is more than this tau c value, then again you have to increase the depth and all. You have to redesign the section. So let's find it out how much is the shear stress applied on our slab. So the values k value you have to compute same thing what we discussed in the one way slab also. In the clause number 40.2.1 we got it k value. So here our k value for the 160 mm depth is 1.28, right? So from tau c we get it this much. So this is our tau c now. So and how much no, vu is applied in our in table 20 if you get it. So shear stress tau c will be tau v will be vu by bd. So already shear stress we computed at 31 by bd, you will get it 0.229 Newton per mm square. Okay, so this much is the how we got it. Vu already we know, right? Vu is what is the formula for Vu? Already we derived it. So Vu is equal to W into Lx square by 2, right? So using this formula we compute a Vu which is nothing but 31 by Bd. Bd is cross sectional area, B is 1 or 1000, 1 into D is what? 135 135 D value by 1000 also, so you will get it Newton per mm square. So this is the applied shear stress applied on a slab. But how much is the capacity of our slab? Our slab capacity is 0.35, so capacity is more, but the applied shear stress is less. So again our slab is safe here also. In step number 4 also it got passed. So now step number 5, determination of area of steel, you have to compute it. Already we know how to do that in the same process what we discussed in the one way slab also. Using the same formula we can easily compute what is the value of for this mx value, what is the diameter of spacing is required. So you can compute it by yourself and these values comes out to be something like that. So for the top negative reinforcement for the lx span, it will be 10 bar is sufficient at the spacing of 20 meter center to center. Similarly for the bottom reinforcement is 8 is sufficient at the spacing of 170 per center to center. So similarly ly also you will get it easily from this expression. So this process we discussed in details in the one way slab design. So same process we continued here. I have not discussed it, but you can refer that lecture and you can understand how we got these expressions. Okay, so that's the minimum reinforcement as per our IS 456 is minimum is 0.12%, right? So let's check whether we provided minimum reinforcement or not. So AST equal to minimum reinforcement is 0.12% into cross sectional area. B is 1000 into D is 160. That comes out to be 192 mm square. But whatever we have provided, it is more than 192 mm square. So minimum reinforcement check also it got passed. So step 5 also completed. So now step 6, selection of diameter and the spacing of reinforcing bars. So maximum diameter allowed as per same process whatever discussed in the one way slab. Also same clause number, it should be 1/8, right? 1/8 of the overall depth D. So overall depth is 20 mm, so we should provide less than 20 bar. Here we have provided only 8 and 10 diameter bar. So again this is also fine. Maximum diameter also fine. So maximum spacing of the bar in this clause it is mentioned it should not be more than 300 or 3 into D, small d. So what we have provided only 170 and 200 so which is less than these two values. So again this is also satisfied. And the maximum spacing of the minimum steel distribution by less than this one, this is also satisfied. So all these criteria we have to check it, and if it is satisfied then only we can proceed and our design will be accepted. So step 6 also over, checking is done. Now step 7 we'll be discussing. Before that, so this is a detailing of the slab, we got it. Okay, so bottom reinforcement, top reinforcement, all these things we have computed it. 8 and 8 tor bar at the 250 center to center. All these charts in the step 5, whatever is seen, all the bars are shown here in details in this figure. So now in the step 7 is we have to provide the corner reinforcement, right? The determination of torsional reinforcement, we have to provide it at the corner C1 and C2. So we have two corners, right? C1 and C2. For the panel 1, it is C1 type. So all this, how many bars you have to provide it? 50% bar at the top, B1, B2, right? All these things I have discussed is in the step. So from that, same thing we got it here also. 50% bar we have to provide it. Same criteria we followed, and these bars are designed. So now that's how we completed a complete two-way slab design from basic scratch. And ultimately this design we have to give it to the site engineer. Now he will make the exact enforcement pattern in the site and he will cast the slab. So that's how we completed our slab designs. One way slab design we discussed, and two-way slab design also in this class we have discussed. So basically you have to provide the reinforcements as per the design, and our slab should be sufficient. So there are basically, you understood two types of slabs are there. One is one-way slab, one other is two-way slab. Depending on the dimension of the LX and LY, we classify the slabs into two one-way slabs and two-way slabs, and the design of slabs are very similar to beam design, where we consider the thickness of the thickness of or the width of the beam is 1 meter in case of slab, and then we design it. So the one-way slab is exactly same as the beam design, whereas two-way slab, only additional thing is that corner tension, corner torsional reinforcement you have to provide it in the two-way slab, because it is trying to uplift the corners. Okay, so that's how we completed the slab design. So in the next class onwards, or maybe we'll be starting the column design. Thank you.